Okay, we're back, and hopefully you've taken these equations and made substitutions for A0, A01, A02, up to A0 n minus 1, and simplified this upper equation to only have 3 unknowns, and these equations to, instead of being 4 equations with 8 unknowns, each being 3 equations with 6 unknowns. Let's write out what you should have gotten on the next slide. This is all being enabled by the fact that we've solved for all the A0 terms. A0k equals yk for k equal 1 to n minus 1. Making those substitutions and then writing down the 3 remaining equations at each intermediate point gives this 3 equation, 6 unknown set of constraints. You can see that we've used A0 k minus 1 equals yk minus 1, and that's why yk minus 1 is now appearing in here, and A0 k minus 1 is no longer on the left-hand side. Similarly, in the equation at the right endpoint, we've made a substitution for A0 n minus 1 equaling yn minus 1, and that's been moved over the other side. So now in these remaining unknowns, we have n minus 2 sets of 3 equations, and then 1 additional equation. Let's collect those up into one large matrix vector system of equations. I'm going to assemble them for the case n equals 6. You can think about how this generalizes, and we'll even cover that a little bit on the next slide. If there's 6 data points, then there must be 5 polynomials. We've already solved for A0, A01, A02, A03, A04, and A05. The only things we need to solve for now are A1 through A3 for each of the 5 polynomials. Remember that there's 3 constraints established at the point between the first and second polynomial, and those can be expressed as a 3 by 6 array multiplying the coefficients of the first and second polynomials equaling a particular 3 by 1 array formed from the y data. This is exactly what we established on the previous slide. That would be at k equal to 2. At k equal 3, a similar array, though involving h2 instead of h1, relates the coefficients in the second and third polynomials to the second and third y data. Moving to the next point, a similar array relates the coefficients of the third and fourth polynomials and involves the third and fourth y data. Finally, at the 5th point, the 4th and 5th polynomials are related, and as expected, that involves the 4th and 5th y data. The final equation we've established involves the last polynomial and its value at its right endpoint. Using the substitutions that we carried out on the previous slide, this equation looks like this. This represents 13 equations in 15 unknowns. Again, we're 2 equations short. So as we mentioned earlier, there's 2 more conditions that we can impose. We can impose the natural spline condition, the periodic spline condition, the not a knot spline condition, or make n-slope specifications. We'll go over what those 4 look like in terms of filling in these bottom 2 rows. Before we do that though, let's look a little bit at how we would do this in general, rather than the n equals 6 case as listed here. The basic array layout would be the same. We can leave 2 rows unfilled in at the bottom. Those depend on which of the conditions we impose. And the coefficients A1, A2, A3 for each of the polynomials would be our unknowns, and those would be stacked vertically. Here I've got the first one, then some space for all the other ones, and finally the n minus first one, which is the last one. The same 3 by 6 array would relate the first and second polynomial coefficients, and so on. Those 3 by 6 arrays would just be dropped in their appropriate location. Let's think about where does the kth such array go. Remember that each array takes up 3 rows, and they do not overlap. Therefore, the row index for this array is 3 times k minus 1 plus 1 to 3k. Think about that. At k equals 1, this goes from 1 to 3. And then as k increases by 1, the starting index increases by 3 and the ending index increases by 3. So therefore it's always going to be correct. 1 to 3, 4 to 6, 7 to 9, and so on. The columns is just slightly more complicated. The first matrix goes from 1 to 6. The second matrix goes from 4 to 9, and so on. The starting column location is the same as the row starting location. It starts at 1 and then moves in threes with each successive k. The ending is what's different. These are not 3 columns, but it's actually 6 columns. So therefore the ending column must just be 3k plus 3. If you think about it, the column index then must be 3 times k minus 1 plus 1 to 3k plus 3. Knowing those indices, you can easily write a for loop to fill in these n minus 2 sets of 3 equations involving 6 unknowns. The unknowns are in the right order so that those arrays are just stacked in exactly the manner listed. And then the bottom equation involves the n minus 1th h and the coefficients associated with the last polynomial. So it's relatively straightforward to automate that in a for loop, and an excellent exercise for you to do in terms of your skills at pre-allocating an array and then using a for loop to fill it block by block as listed here.